The last integral we have to deal with, this one, is very problematic because it is problematic at both ends. To begin with, at 1, because the logarithm of 1 is 0, so it's 0 in the denominator, right? So it might be a problem. It's true that the denominator is also 0, but still, I mean, we have to see what happens in this limit here. The other limit, of course, is problematic because the logarithm of 0 is infinity, and up here also if p is negative, then this function in the numerator is divergent. So we have problems, or we potentially may have problems in both limits here. All right, what we're going to do is to get rid of the logarithm by doing a change of variable in this integral. And the variable we're going to introduce is minus the logarithm of x. And the reason we put a minus here is because when x is between 0 and 1, this logarithm is negative, right? So t is going to be a positive variable. So that's the only reason why we write a minus there. So from this we have that x is equal to e minus t, or dx is equal to minus e minus t dt, right? And then what we have to do is to transform the limits and the arguments of this integral here. So we have with this minus, we are going to compensate the limits, right? Because when x is equal to 0, what we have here, the logarithm of 0, it goes to minus infinity, with this minus to plus infinity, so we will have a plus an infinity here. With this minus, we put it here, okay? And then, when x is equal to 1, then the logarithm is 0, so we would have an upper limit 0, which with this minus we put it in the lower limit. So we have compensated with this sign. Then we have this exponential, right, e minus t. And then we have to substitute here. So we have x, which is e minus pt, minus 1 divided by minus t dt. So if we write this a little bit more easily, what we have is, well, we multiply the two exponentials, and then we have 1 plus pt, right? Then we have here e minus t. Well, actually, we're going to compensate with this minus, so we write the exponentials in reverse, like this, okay? And then we can put just t in the denominator. We use the minus to interchange these two numbers, or these two expressions, right? And then we have this. Okay, we can split this integral in two because we may have a potential problem at 0 and another one, of course, at infinity, right? So let's separate this integral between 0 and 1. So e minus t minus e minus 1 plus pt plus t divided by t, and then the integral from 1 to infinity, e minus t minus e minus 1 plus pt over t dt. All right. Now let's focus on the first integral here, right? This first integral. And let's see. No problem at 1. The only problem would be at 0. It's potentially at 0, but however, at 0, what we have is, well, this function here, e minus t, is equal to 1 minus t plus ot when t goes to 0. And likewise, e minus 1 plus pt is equal to 1 minus 1 plus pt plus ot when t goes to 0. And if we subtract them both, then we have to subtract this from this. The 1 cancels, and then we have minus t plus 1 plus pt plus ot, which is just pt plus ot when t goes to 0. Which means that if we have this function divided by this t here, and we expand, or we try to find the Taylor expansion when t goes to 0, we just have to divide this by t, and then we have p plus O1. when t goes to 0, which means that this function is continuous at p, at 0, right? It just yields the value p. So actually there's no problem of this function at 0. This is a well-behaved function everywhere in the interval 0, 1. So this is an ordinary Riemann integral. So this integral, of course, converges. No problem. Now let's focus on this one. Well, actually this one can be split in two integrals, right? Because now you don't have the problem of the 0. I mean, the denominator is never singular anymore because we're integrating from 1 to infinity. So this integral here can be split as the integral from 1 to infinity of e minus t minus 1 dt, right? Minus the integral from 1 to infinity e minus 1 plus pt t minus 1 dt. Now this integral here converges. We have analyzed that several times, right? For any exponent that you have here, this is a convergent integral, and so is this one. Actually, if you want to transform this into this, all you have to do is to make a change of variable, 1 plus pt equal to s, for instance, and that would transform the integral into something which is proportional to an integral of this type. But maybe with a different limit here, but that doesn't matter, right? As long as this limit does not include 0, and it won't, then it doesn't matter. So this one is going to be finite too. So actually 3 is a finite integral, it's a convergent integral. So this integral converges, right, for any, well, actually converges for any value of p larger than -1, because when this happens, p plus 1 is a positive number. And of course, this is a convergent integral, I forgot to mention, if and only if 1 plus p is a positive number, because then this is a decreasing exponential. Otherwise, if this is 0 or is negative, then this integral diverges, right? So actually the constraint here is very important. It's very important because it guarantees that this integral here is going to converge, right? So yes, for this region of parameters, of this parameter, this integral here converges.